problem that I'm going to discuss today is in collaboration with Nao Murashige, and much credit should go to him. He did the most of the work, and I'm just presenting the result. So anyway, all right, so this is the outline. This is the talk about the stability of periodic waves, and so it's very simple, just usual story. Okay, so I have to start with the motivation. And a few years ago, I had a chance to do some experiment with many Japanese people in Korea. It's a very strange combination, but we did that. Okay. Anyway, so this is the experiment for internal solitary waves, periodic waves. But you can think, this is periodic waves with a long wavelength. Okay. One thing that we noticed was, we always see some wiggles on the periodic wave. So at that time, I wanted to understand, this stability or perturbations. So that's the motivation of this work. And in this case, just to explain this, this is a wave of depression, and we use, the water here and silicone oil. It's basically 2 immiscible fluid. That's why. Okay. So this is a problem. Sorry for very unprofessional drawing. I realized that my drawing is worse than Word's drawing. So yours was a smooth, mine is not. But that's okay because I'm talking about waves with the perturbations, right? So this is exactly what I'm going to talk about.
Help us stability.
Yeah, but I need the perturbations to study instability. So little wiggles on the periodic waves should be okay. All right, so this is the problem. So I'm looking at 2-pi periodic problem, and the gravity is acting downward, and I assume density in the lower layer is greater than upper layer. So static, it's a static, stability. So there is no Rayleigh-Taylor instability. Also, I don't have any background shear. Okay. So it's different from classical carbon-harmonic instability. So if I don't have a wave, then it's flat and nothing, okay, no motion. So the motion starts once I lift, the interface, if I can. What else should I say? Zeta is my interface between 2 fluids. All right. So what if I give a long wave perturbation? What happens? Everyone knows in this room, modulation of instability. So we expect that. What happens to I perturb, the interface with the short waves like that? We also know for surface waves, but we don't, care much about this for surface waves. There are 2 reasons. Okay. One is the growth rate is relatively smaller than growth rate for this problem, and secondly, the instability, shortwave instability can see only for small range of parameters. Okay. So practically, it is more important problem than this. That's the story about the surface waves. But now, question is, what happens with internal waves? So internal waves, the one thing that we should remind ourselves is, because the grad rho is density and grad p is pressure, they are not aligned, parallelly. Because of that, once you start to move, the interface, the vorticity can be generated along the interface. We know that. Okay. So because of that, locally, we have the velocity discontinuity. Of course, the discontinuity, velocity jump depends on space. So that's a little different from classical. All right. So, but locally, we expect, Kelvin-Helmholtz instability because, this variation of velocity jump can be has a length scale of lambda, which is 2 pi, And the perturbation length scale is much shorter than that. Because of that, the two disturbances, the variation of a velocity jump is negligible. That's the argument. Okay, so as we know, the Kelvin-Helmholtz instability has a very large growth rate, first of all, and could be post. And so what's happening here? But we already know, it'll be unstable and it'll be it has a very large growth rate. So in other words, this problem for interface problem, this is more important than this. Okay, I think. So that's the story that I'm going to tell you. So I can stop here if you want to, because that's basically the conclusion. But I have to give you some details, so I'll go through some details. Okay. What has been done before? Here, there are many people involved. Jean-Marc. Whenever we want to study, steady wave, we have to ask, Jean-Marc, right? Who else, right? So Jean-Marc made a lot of contributions to compute steady waves and so on. So we know that. But strangely enough, there are not many papers on the stability as far as I know. Several. Most of them are looking at the stability of small amplitude waves. For surface waves, we know that there is a long history of studying, instability of large amplitude waves, but for interfacial waves, there are many. In fact, these are the two papers that I'm aware of. They try to study, the large amplitude interface, stability of large amplitude interfacial waves. I might be wrong. Just correct me if I am. But I couldn't find, many papers. In the first, experimental picture, the wave amplitude is very large compared with any scale that you can pick. Horizontal, vertical, amplitudes are large. So we need to know what's happening when the wave amplitude is large. Although we kind of know, the wave would be unstable due to the Kelvin-Helmholtz instability. So in the literature, what is missing in the stability of interfacial wave? First of all, many papers have focused too much on modulational instability. It's kind of understandable, right? Because around that time, Benjamin Fair instability was everything. So people wanted to generalize, that approach to interfacial waves. So that's what people have focused on. And so small number of results are available for Kelvin-Helmholtz instability induced by interface deformation for interfacial waves or internal waves. So I'll give you a couple of examples. There are two papers. They try to solve full Euler equations to understand the stability of interfacial waves. So UN, they solved the problem for these two particular stiffness, K being wave number and H being the wave height. So 2 times the amplitude. But these numbers are much greater than the what you normally deal with surface waves. So interfacial waves have a large amplitude. At that time, they use small number of Fourier modes. He did the spectral analysis, and they use 20 Fourier modes to compute steady waves, and 5 Fourier modes to compute the spectrum. Very small. Also, wave amplitude, the stiffness is larger than what we normally deal with surface waves, but still smaller than the very large amplitude internal wave, interfacial wave. But it's understandable because their formulation is based on the physical, everything was done in physical space. If amplitude steady waves has a very large amplitude, then you cannot handle that in physical space. You have to use, some other transformation to deal with that. But they tried to use, the physical space and so on. So they had some issues, okay? To compute, steady waves and then compute, eigenvalues. Later, Cooley and Grimshaw handled, much slightly larger amplitude stiffness wave under the Boussinesq approximation. That's fine. But, if density difference is large, then they cannot handle. Also, this is the only wave stiffness that they can, they showed. Okay. Probably they did more, but anyway. So one of the issues, as I said, the stability problem has to be formulated in a different, not in physical space, but in transform space. And also the numerical method has to be accurate enough to handle, all those things. So what should I do? This is the only thing that I knew at that time. So this is what I call, unsteady holograph transformation. Although whenever I write, paper with this name, someone complains. This is not really holograph transformation. Classical holograph transformation, where you change it, you use phi and psi instead of x and y, right? That's the transformation that you use. But this, when you, okay, so what is this method? This method is you are trying to solve this physical problem in transformed plane. And you always map to the strip, but we don't know the mapping every time step, right? So we have to find that. Basically, these evolution equations is the system to find the mapping. Basically, okay, that's what we are doing, right? So because of that, this is to me the unsteady generalization of the holograph transformation, because when I take the steady limit, I will get exactly the classical holograph transformation. So, but anyway, the name is not important, and this formulation has been done, several people, these two group actually, and much credit should go to Dyachenko et al. Because they really advertise the method to compute unsteady problem. But original formulation was given of Shyanikov 1974 paper. So but they really used they didn't cite this paper, but they really tried to use this method to compute unsteady waterway problem. Okay, so I knew that. And so I used this to study stability of large amplitude waves. Okay, because it's a perfect model of the stability of large amplitude. Here is a connection, my connection with John Mark. If I give you this story, John Mark wouldn't remember anything, but that's fine. So when I worked on this system, I wrote a pseudo-spectral code, right? I wanna make sure that my code is working right. So what do? I put the exact solution, right? The only exact solution that I know analytically is Krapper solution, right? So I put a Krapper solution as initial condition. I let it go. Normally, when you solve highly nonlinear PDEs or not integral differential equations or whatever, you always see some problem, right? With the pseudo-spectral method, aliasing and all kinds of things, right? For some reason, when I solved this for Krapper solution with the capillary waves, I didn't have any issue at all. So I said, oh, I'm very good. Okay, I must be good, right? Otherwise, I should see some issues, right? So then around that time, I met John Mark at the APS meeting, I assume, many years ago. So you probably don't remember. So at that time, I asked, John Mark, do you know anything about the stability of Krapper solution? And he said, he didn't know. he should be the one who knew, that property, right? But he didn't know. So I said, oh, okay, then that might be something that people haven't done. But it's a strange, right? The proper solution has been for a long time. How come, nobody looked at it? The reason is, people try to use, physical plane approach, and which wouldn't work because this wave is too highly nonlinear. But with this kind of a system, you can handle that. So that's the why I started to work on stability of periodic waves, and all credit, some credit should go to Jean-Marc because he didn't know the stability, and he said, why don't you study that? Okay, so okay, so I can do that. So that's the problem. But the reason why I didn't see any instability when I ran the code was, the Craft solutions are always stable to super harmonic disturbances. Okay, that's the fact that I learned later, and I always solve, the equation with one period, and so I didn't include, the modulation and instability, okay, because I only have one wave, and perturbations are always have a shorter waves, and so that's why I didn't see any instability. Not because I'm good, but the Craft solutions were stable to super harmonic, disturbances. So that's some connection. Yeah. So I have a good reason to present, this. All right. So since then, I worked on the stability of periodic waves. I spent too much on something else, as usual. Okay. But the technique is already known. So basically, this is two layer, upper layer, lower layer. I map into the half plane, up and lower half plane. And then all I have to do is just rewrite the equations with the subscript J equal to 1 is upper layer, 2 is a lower layer kind of thing. So I will skip that. The only thing that I have to mention is, when you do the two component mapping top and bottom, and then you have to glue together, the question is how is the question. And so just let me briefly mention, we introduced auxiliary variable gamma, and then we could do it. And so really, matching conditions are the condition the two waves should really meet at the physical plane. That's basically what it is. And also stream function must be continuous to compute, but similar ideas were applied to, steady and unsteady waves by different people. Okay. So this is the results that the Snell worked very hard. Yeah. But anyway, so basically there are some solutions. Waves can be the amplitude can be much higher. But this time, we focused on instability instead of a steady solution. So we stop computing over there. If you need any higher amplitude waves, you can ask Jean-Marc to compute. He can do it. Okay. But anyway, so this is the fifth order approximation Stokes expansion for interface problem. And as amplitude increases, you start to see something funny, and so you shouldn't use the Stokes expansion for large amplitude interfacial. Okay, so we got the steady solutions. Oh, to make sure that the solutions are not really bad, somewhat okay. I wouldn't say great, but here we plot Fourier coefficients with n equal to 128. That's the typical Fourier mode that we use to compute, and we use the 10 to the minus 16 double precision, so it's right there. So we could really resolve everything up to there. If I want to resolve higher mode, then I have to use a quadruple and so on, higher precision. But we decided to use a double precision, so everything is good. And also we increase the number of Fourier modes. We double the Fourier mode to see, whether the Fourier coefficients are, conversion or not. So apparently they do, and so on. Okay, so now we have steady solutions, and the steady solution have a discontinuity. So this is a velocity jump. So usually you see the biggest jump over the crest of the wave. That's what we expect. I mean, we already know. All right. So we should see some instability above it. Okay. Linear stability analysis. And this is a standard again. We have a steady solutions and we just perturb it linearly. And then linearized problem, use Floquet theory, and everything is very standard nowadays. So I wouldn't discuss much. And earlier the talk, P it tells you whether the perturbation has a longer wavelength than the periodic wave or not. So if P is 0, then you don't have any, you have only short wave perturbation. But anyway, so these are the standard one. And at the end of the day, you end up with a generalized eigenvalue problem, as you can imagine. The point here, the one thing that I want to mention here is, perturbation is not really one single wave number, right? Because we are using Floquet, and the background wave is a steady wave, has a large, the bandwidth, and therefore you cannot have just a single perturbation, right? So I have to compare with something else. I have to figure out what is the dominant mode. And I don't have a very clever idea to pick, dominant mode. So I just looked at the Fourier coefficients, and whatever I see maximum, I give that mode as a dominant mode. Okay, so mu is perturbation wave number for perturbation. So sigma is eigenvalue or growth rate. Depends on 4 parameters. This mu is the wave number for disturbances. T is the wave number for envelope, if you want to say. And these two are the physical parameters. H is wave height, 2 times the wave amplitude, and density ratio. Okay, so these are the 4-dimensional space. And so to pick even mu, if I see wave eigenvector, and if I see the largest one here, I realize that this happens at m equals to 1, then mu is 1. That's how I chose the dominant mode. But in some cases it's not clear what is dominant mode here. If this is vectors versus the eigenmodes. And in this case, it's rather broad. So it's not this, classification is not so so good. But still, I use this, and then this guy has a maximum growth, the amplitude. So I said this guy is a dominant mode. Okay, so that's how I chose mu. Okay. At the end of the day, this is what I'm going to plot. So far, so good. Maybe not. Anyway, the numerical solutions. The plot is not so good. So this is a sigma, again, versus, it depends on these 4. And this time P is fixed. So for example, here P0, so there's no perturbations in, whose wavelengths are greater than period 2 pi. Okay, everything is shorter than that. And then density is fixed. And then this guy depends on mu and h. Mu is a dominant mode wave number, and h is a wave height. Almost 0 here. All of a sudden you start to see instability. So this red line can be the critical wave, critical line beyond which expect instability. And also the instability growth rate increases with the wave number. Apparently, it looks like without bound, which means the problem is still ill-posed. But that's the definition of ill-posedness. If the growth rate increases with the k without bound, then I expect the ill-posedness. Okay, this is example. And usually what we do plot is we cut this, right? So we fix wave amplitude and then see what happens. And then we see we can growth rate versus wave number. That's what we normally plot. Since I'm looking at short wave instability, the classical Kelvin-Helmholtz analysis might be relevant. Although the velocity jump is a function of space, but I can start to use the Kelvin-Helmholtz instability. This result can be seen in any book nowadays, and that tells you where the critical wave number is. So we compare that with the numerical solutions. So that represents the numerical solutions, and the red lines represent local analysis based on Kelvin-Helmholtz instability. And what it tells us is the local analysis without neglecting the variation of a velocity jump is good in terms of the prediction of criticality. But the growth rate cannot be estimated from the local analysis. That's the message that this result tells us. We can do more by changing the density ratio. So this is 0.1 is closer to surface waves, and then this is 0.9. So in this case, density jump is almost negligible. And as we expect, density difference increases, we have a stabilizing effect, right? Because density difference gives you a stabilizing effect. Gravity always gives you a stabilizing effect, but the density jump is small like this, then the stabilizing effect is weak. Because of that, you see the larger domain of instability. Okay, that's what happens. All right. Since I have 5 minutes. Sure. Okay. Since modulation instability is one of the topics here, so we also looked at that, and we also compared the numerical solutions with the NRS type, the analysis. And once again, we compared the numerical solution with the NRS model, and the red curves gives you the NRS model. So the message again here is the NRS is a weakly nonlinear model. Therefore, you cannot really use for interfacial waves because the amplitudes are very large. And also we did a numerical computation in the physical plane as well as what others did. And then they are good actually. You can do it for small amplitude waves, but if you really increase the wave amplitude, then the formulation in the physical plane is not good. Okay, so that's the message. So you should use a steady holograph transformation to do proper stability analysis. Okay, one more slide. So previously, this slide, this amplitude is 0.7. The lambda is 2 pi. Okay, so you can compute k times h, but still large. But if I further increase the amplitude, that's what happens. So first of all, the numerical results in the physical plane space is not good. So I just want to point out that. And And the other thing that I want to point out is, there is something here. Okay, so when Snow showed, this result, I wasn't comfortable, right? I see something in the middle. What is this? I have never seen something like that. So I thought, this is the numerical artifact or something, right? So I torture, Snow in different ways, to check this, to check that, right? But apparently, this guy persists. So I wasn't quite comfortable to present this in a paper, but finally we did. Okay. I still don't know where these guys came from. So let me know if you see anything like that in the modulation or instability. But
No, I mean,
I looked at the Yuan's paper published in 1984. Of course, I criticized that they didn't use many Fourier modes and so on. But now I rely on this. But they did a two-dimensional computation. Yeah. And also they had a background shear. So this is slightly different. I don't have any background shear, right? But they do have a background shear. So it means, if you have a large shear that you put originally, or large shear induced by large amplitude waves, then this might happen. Okay. Why? What? I have no idea. Okay. So don't ask me. I'm just telling you. So this is a two-dimensional computation. So they have a px and py, but we are doing 1D computation. So you just look at this line. This is usual, modulation and instability, and then they start to see something here in between these two numbers, which is what we see here, between here and here. So, but anyway, so that's something that we couldn't explain, when we wrote a paper. So if you think we made a mistake, let me know. If not, then please explain to me. All right. So this conclusion, I already discussed this, and then okay, our computation is okay, not super great, and you still need to increase number of Fourier modes to really compute large amplitude or extreme amplitude or amplitude close to the maximum. So there are a lot of room to improve in terms of computation. Also, as I said, this problem seems to be still posed, just like the Kelvin-Helmholtz. So density stratification is not strong enough to eliminate that. The nonlinear evolution of unsteady short waves remains to be investigated. Meaning that, okay, if I don't have any density stratification and the velocity jump is constant everywhere, then we know what's happening. It's a vortex sheet problem. Local rotation tells everything. You know that when the singularity forms and so on. Now we don't have a constant velocity jump. And also these waves that don't have a zero mean velocity. Okay. So because of that, we might see the same thing as the Kelvin-Helmholtz problem, classical Kelvin-Helmholtz problem without density jump and so on. But we might see something different. I do not know. Okay. And in the experiments, we see perturbations, disturbances growing, but they don't grow forever. Of course, you can blame, I didn't include viscosity here, and the stratification is not really, very sharp and so on. But still, there is something that I do not know about the nonlinear evolution. So that's something that I'm interested in, or I want to see the result. So I just put those two for the future work. All right. So this is the paper that I wrote with Rafidia last year. So if you want to know little details, you can take a look. All right. Thanks.